Aloha, Richard Halverson here, and we're going to finish up the chapter on graphs for this semester. So we're going to look at Dijkstra's shortest path. So let me share my screen. So we're doing section 21.12 of this textbook. It's the Dijkstra's shortest path algorithm, and basically what Dijkstra's shortest path algorithm does is it figures out from a particular node or vertex. We're looking at a weighted directed graph, and it figures out the shortest path from a starting vertex to all the rest of the vertexes. Okay, and the way it does it is it builds this. It keeps track of two variables, two properties for each of the nodes, and what it is it's a number and a node. And what the number is, what the number is the distance from the node back to the starting vertex, and the node is the direction to go. So, for example, here we have node vertex C, and it says that and you know, this is all filled in now. So you go through this algorithm here and follow this. And so this is the finished data for these vertexes. And so for C, for example, the distance back to A, the shortest distance back to A is 6, and it's by way of D. So you go from C, you go back to D, and this is, and for here the distance is 4, and you go by way of B, so you go back to B, and here the distance is 3, and you go directly back to A. So you see that the shortest distance from A to C is not down here. It's not from here to here. It's not even from here to here to here. It's from here to here to here to here. And that's because the weights here are smaller. You add up this weight, 3 plus 1 plus 2, and that just equals 6. And that's how they get the 6 here. So Dijkstra's shortest path algorithm runs, it executes on a graph like this, and it figures out what all of these values here for all of the nodes. And once you have that, then you can figure out the shortest path between the vertex and any of the other vertexes. So we see the way it does it is it starts out by loading up this queue called unvisited queue, loading it up with each vertex, and setting all of the values for all the nodes, the initial nodes, to infinity, meaning that it's infinity steps back to the vertex, the main vertex, and null means there is no, we don't have a direction yet. And so, okay, so and then what we do is we set the starting vertex, we set that equal to 0, and then all of the unvisited queue here, it's all loaded up, and this is set to 0. And what we do is each time we pull a vertex out of the unvisited queue, we pull the minimum one, the smallest valued one. So the first time we do it, there's 1 0, which is A, and then all the rest of them are infinity. So the first one you pull out is going to be A, obviously, and then you go through, and from A it's 0. You go to B, and we now know that B is 3 back to A, and this is an A, and C is going to be 7 So this is going to be become a 7 back to A. Oops. So if we go to the next step, we see that that's what happens. It sees that 3 is less than infinity, so that gets replaced with 3 and A, and then for here it sees that 7 is less than infinity, so this gets replaced with a 7 and A back to A, and this keeps on going until all of the. Now what can happen, of course, right now this is 7 and A, but as we keep on going, we will find when we process, which one is it? It's not done yet. We'll find that when we process D, that we find that 3 plus 1 plus 2 is less than 7, and then the 7 is going to get replaced with a 6, and the A is going to get replaced with a D. We see that. We're processing D, and we find that 4 plus 2 is less than 7. 4 plus 2 is less than 7. So now we replace 4 plus 2, which is 6. 6 goes there, and the D goes there. So that's how this works. You can click through, make sure you click through all of it. And here tests your understanding of just how the shortest path, how it's built, distances and so on. Determine the shortest path. This is using the results from Dijkstra's shortest path algorithm. For example, here, after executing Dijkstra's shortest path for E, what is the shortest path from E to G? Okay, well, we go to G, and we want the path from E, the shortest path from E to G, and Dijkstra's shortest path algorithm was executed on E. Okay, well, what we have here is we have 13. It's 13 it's a weight of 13 back to E. And which way do we go? Well, first we go to J, and that's down here. And then we go to F, that's over here. And then we go to H, which is down here. And then we go to E. So you see the path is, let's see if this works. The path is for E to G, it's G down to J, down to F, down to H, down to E. And that's because each of these, this says go to J, this says go to F, this says go to H, this says go to E, and this goes to E, and so you can see that's how that works. So the answer is would be shortest path is going to be E, comma H, comma F, comma J, comma G. Yes. So anyway, that's how that works. We can have negative weights. Okay, let's do these. Okay, the first one. Starting at vertex D, what is the shortest path length to each vertex? Starting at vertex D. So if we're starting at D, what's the shortest path length to each vertex? Okay, to A, it's going to be 6. And from D to B is going to be, I go to 4, 6. So I guess I have to go down here and then go up to here. So that's 10. 10. From D to C is 9. From D to D is 0. And from D to E is 4. I think that's the shortest path for each one. There's no fancy way to get to 665. Okay, check. Very good. All right, what's next? Dijkstra's shortest path algorithm is run on the graph starting with vertex B. All right, should I execute? Should I actually do it? I think I'm gonna actually do it over here. Well, actually, what I think we can do, all right, we're starting at C. Let's see if this works. We're starting at C. Oh, gotta do. Oh, I gotta do this, then I got it. Okay, starting with C. The shortest path to A is okay. The shortest path to E is 3. So this is going to be 3C, and the shortest path to D is going to be, see, it's 4, 5, or 4, 5. Got to be 4, 5, 4, 5. So it's going to be D is going to be 9, comma A, and A is going to be 4, comma C, and B is just going to be 5, comma A. All right, so to get to can I do another color here? To get from C to E, you just go like that. I guess it doesn't. To go to C to D, you have to go to A and then to D. And from C to A, you just go down here, and from C to B, you have to go to A and then to C. Okay, so the answers are, let's see, I don't think I get to keep those, do I? Let me just so really it's B is B. B is 5A. C is 0, nothing. E is 3, comma C. Three, comma C. D is 9, comma A, and A is 4, comma C, and this is 1, this is 5, this is 3, this is 5, this is 4, and this is 4. And this is 5. I should put circles around these things. All right, anyway, so go back here and let me get rid of this thing. And so the answer is upon completion, what is each vertex predecessor? Okay, so A's predecessor is C. Hope I did this right. B's predecessor is A. And C's predecessor is null, I guess. There's no predecessor. D predecessor is A. Basically, I'm talking about these here. These are the predecessors. And E's predecessor is C. See if this is right. Very good. All right, here's the last. Okay, here we do Dijkstra's shortest path algorithm from E, and we're going to be executing the algorithm, and we figure out which one is dequeued each time. So they're dequeued in order of the smallest distance value here, the property. I'm going to start over again. Let's see, I'm gonna make this look a little bit better. I'm gonna go B, B, E, C, A, D. And we have a 4. And we have circles. 4, 9. And we've got 1. And we've got 10. And we've got 2. 2. We've got 8. And we've got 7. Okay. Okay, good. And we're starting from E. Starting vertex is E. That's a start. Okay. So we're first thing is we're gonna set all of the I'm gonna start with red here. They're all infinity null, infinity null, infinity null, infinity null, infinity null, and infinity null. That's how we started out, and but we set the vertex for the starting vertex. This distance is 0, so that we change that to 0. Erase this and make it 0. Okay, so now the first one that's dequeued then is going to be the smallest one, and it's going to be E because E is 0. Fix this. So this one's going to be E. That's dequeued, and then which vertices are updated because we're processing E? Well, let's see. B is going to be updated, and this is going to turn into from E to B this is going to turn into 9. And this is going to turn into E. And that's so 9, since it's all the adjacent, it's all the vertexes adjacent to E. And the next one is going to be this one. C is going to be updated. So it's 10. This is going to be replaced with a 10. 10. because it's 10 to E, and this is going to be replaced with an E. Okay. All right. So I got to put here B and C. All right. What vertex is DQ'd next? Well, it's the smallest one, which is, slide this over here. It's the smallest one that hasn't been processed yet, and that would be the 9. This is the 9. So the next one is going to be 9. This is the next one that's processed. Because of the 9. So we're going to put the B here. And when we process B, which ones are updated? Well, D is going to be updated, and C is going to be updated because those are the two that are adjacent to B. So let's go to C. 9 plus 1 is 10. Is 10 less than is 10 less than this 10? No, it's equal to. So you can get to C by going 9 and 1. 9 and 1. Or you can go to C, go directly. So we don't change. We don't need to change C. So C does not get updated. What else about this? D, yes, D does get updated because infinity is definitely bigger than 9 plus 4. So 9 plus 4 is 13. Erase this. This is going to be 13. 13 slash B, because it comes from B back to B back to E. Okay, so that's updated. D is updated. Okay, what's next? What's DQ'd next? It's going to be the smallest one that hasn't been visited yet, and that would be 10. That would be C. So the next one that's visited is DQ'd is going to be C. And which vertices are updated when we process C? Well, A is certainly going to be updated because it's infinity. So to get to A to get from E to A, you going through C, you go 10 and 2, so that's 12, and this is going to be C. So I'm going to put 12 slash C. So A is updated. A. And how about D? Is D updated? Right now, D takes 13 to get from E to E to B to D is 13. If we went through C, it would be 8 more from C, and that'd be 18. Nope, don't want to do that. So we do not want to update D. All right, very good. So what's next? The smallest one that hasn't been visited, that would be A. A is only 12. So let's look at A. And what gets updated as a result of A? Well, A has no arrow going out, so it doesn't, you can't get to E from A. So nothing. I got to put none, right? None. Okay, none. And then the last one that's DQ'd is going to be the 13, which is D. And is there anything updated? Let's see. What are all the vertexes that D touches? Well, D touches A. And so if we go, right now, A is sitting at 12. Takes 12 to get from E to C to A. If it went through D, it would be 13 plus 7, which is 20. That's way too big. So again, we have none. Oops, lowercase, just in case it's picky. And let's see if this works. Yes. Okay, so I have finished up the all of the sections of the chapters that I'm going to do this semester. And so the last thing you have to do is the Dextra's lab, the lab number 6, which there's a video, I made a video a few weeks ago for that. So you should be able to get through that pretty straightforward, pretty easily. And so that's it. I'll probably make one more video after this to tell you what you need to do to clean up if you have any issues like need more time or that kind of thing. But anyway, have a good rest of the semester, and thanks for watching.